Okay, so last time we talked about the CHSH game or CHSH experiment, which was like a physically achievable experiment you could do that actually demonstrated quantum advantage. I mean, some kind of information processing task that really could be done fundamentally better with quantum than with classical behavior. And now that we've seen that, like, it really motivates us to get into this, exact question of quantum advantage. I mean, doing things with like more than one qubit that really, are truly quantum and that you can't do with classical experiments or classical computers. So we're going to get into that starting now or in the future. But actually today we're going to start with a negative result or a no-go result called the no cloning theorem, which is about something that you cannot do quantumly. But it'll be kind of like a foil. It'll be like a good thing that will like motivate this further topic of quantum teleportation, which is kind of like another magic trick that Alice and Bob can do with quantum bits, but like one that's actually used in the design of quantum computers. And then we'll get into more things that you can do if you have tons of qubits, like quantum money and quantum key exchange, and then of course quantum computing. So that's the plan for the next few lectures. But let me start with this topic, the no cloning theorem. So this is it's a mathematical theorem giving a negative result for quantum information processing, or what's possible according to the laws of quantum mechanics. It was shown by Wouters and Zurek in a paper in Nature in 1982, so quite a while actually after quantum mechanics had been established. And it just says the following. It says there's no physical device that does the following picture. Okay, you want hypothetically to have a device, some kind of box, which will be like a quantum circuit, that takes in a particle in some, let's say a qubit, in some state psi, and outputs 2 copies of psi. Okay, so it outputs 2 particles, and the joint state should be 2 copies of psi unentangled. Okay, so this is something that you might want to have. Let me just add for all, let's say, qubit states, psi. And of course, if you had this, then you could use it a bunch of times and not just get 1 copy of psi, but as many copies of psi as you wanted. You might feel that this is different from, the classical world, and in a sense it is. I mean, you can certainly build like, a logical circuit that like, you feed in 1 bit and then it outputs a stream of copies of that bit. I mean, you just copy 0 to like lots of zeros or 1 to lots of 1s. That seems fine. Actually, as we'll eventually see, this is not, this fact that you cannot clone qubits like this is not inherently a quantum feature either. There's a version of this theorem that also holds for just probabilistic bits. So in that sense, it's not so strange, it's not so specific to quantum. So this is actually a mathematical theorem. It says, according to the laws of quantum mechanics as we know them, just mathematically you cannot accomplish this. And in fact, the proof is very easy, as we'll see. It's a very simple proof, but maybe it has a somewhat interesting philosophical meaning. And one thing that's quite important I want to emphasize is that it's very important to understand exactly the statement of the theorem, or exactly what it is that you can't do, because there are similar looking things which you can do. Okay, so you have to be very careful to say exactly what is this thing that's impossible. Okay, and this is one aspect of it which is quite important. It's supposed to work, this hypothetical machine, cloner, is supposed to work for all qubit states simultaneously. So what do I mean by that? Well, for example, here's something you can do. There's no trouble like building a physical device that I might call it a zero maker. It's just some machine, and it's got like a button on the side, and every time you hit the button, like a qubit comes out in the state 0. Okay, there's nothing in the laws of quantum mechanics that prevents such an object from existing that like makes many clones of 0. And indeed, we already like talked about this, even in lecture like 2 or something. If you want to make your qubits with photons, then at a high level, you could implement this by having like a laser pointer, and the button is attached to the laser, and then maybe you have this like horizontal filter here that has the property that if a photon comes out of here and it's measured in such a way that it's 0, then it passes through. Okay, so there's no trouble in life in making like a machine that generates qubits in the state 0. And similarly, there's no trouble in, so this one's A-OK. There's no trouble in having like a 1 maker that just also has a button and it shoots out particles in the state 1. That's fine. You can have any qubit state. Like you can have a plus maker. That's fine. Okay, I mean, you can get this by turning your filter 3/4, diagonally. But what's impossible is kind of this thing, which you might call like a. Okay, this picture is slightly different from this one. I'm imagining like you have a button and you press it every time a particle comes out in the state. What's impossible to have is like an input maker. Okay, that's what this no cloning is saying. Which sort of says, you can actually feed in a qubit, any old qubit, and then like have a button that when you press it, it shoots out like multiple copies of psi. Okay, this is the thing that's impossible.
But you can do it, for example, if you guarantee that psi is only 0 or 1.
Yes. I'll mention that in a second. If you want an input maker that doesn't clone any possible input, but like only clones it if it's, or you have this object, if psi is promised to be either 0 or 1, then you can build this. How would you build it?
I mean, you measure it in the 0-1 basis, and then basically you generate the same one, like the same output as you get.
Exactly. So it's using the fact that the 0 state and the 1 state are perfectly distinguishable. As was said, if you promise this is 0 or 1, then you can just like measure it, have like a measuring device in here, and tell if it was 0 or 1. And then you know whether you're supposed to be shooting out 0s or 1s. You can just like put a copy of this box inside, and put a copy of that box inside, and then just use one, whichever one you need to use. Yep?
Is it possible to have an O1 input maker? So like for any fixed n, we can clone n in different states, but not some state in between things.
No, it's going to turn out that you can only have this kind of successful thing when the possible psis that you might successfully clone are perfectly distinguishable, which basically means they're orthogonal states.
So you cannot even do that for like 0 and plus state, right?
Yeah. Do you have a question?
Answered by that.
Okay. Good. So in particular, one thing that this theorem implies is what you might call unlearnability of a qubit or a quantum state. And let me emphasize in words, from one copy. So in other words, if you have like one particle in a qubit in an unknown state, and you only have like one copy of it, which is what we're imagining here when you're hypothetically feeding in this particle to a cloner, there's no way for you to learn its two amplitudes, alpha and beta. I mean these complex numbers, to perfect accuracy and correctness. Because if you could somehow take this copy of psi and learn alpha and beta, in other words, learn psi, well then you'd know exactly what psi was, and then you could just build a box that generates copies of psi. Okay, so let's say you were nevertheless optimistic. You might say, well, I want to build one of these things. What about using a C0 gate? To the extent that there is anything in the quantum world, any quantum gates that are kind of like copying or duplicating, the C0 gate is it. So you might just say, yeah, what if I just have a C0? Okay, so you might think, okay, what if this is my hypothetical cloner? And, draw it as like a little circuit diagram. Let's say it needs to like have output two particles. So let's say it generates a particle on the inside of the box here, and without loss of generality, say it generates it in the state 0. You might think, yeah, like what if I just do a C0 here like this, and that's my output. does this work? Well, let's analyze this. Okay, well, let's consider the possibilities for the inputs and outputs. So let's say the input psi is 0. And what is the output? Well, we do a C0 between 0 and 0. You'll just output 0, 0. Great, that's what you're supposed to output. And what about 1? Well, you're doing a C0 to 1, 0. The target, or the control is 1, so it does the naught to the second bit 0, so it outputs 1, 1. Great. So it looks like perhaps that you're done. If I could, fake a positive conclusion by saying, oh, and then by linearity, like the right thing happens to every state, input state psi. Of course, that's wrong. Although it does show that you can build, as we said before, you can build a cloner that if you're just restricted to trying to clone zeros and ones, okay? That's like kind of the analog of like a classical machine that like takes in a classical bit and outputs, as many copies of that bit as you want. That certainly exists. But what goes wrong is, let's say you now plug in plus. I mean, your desired output is plus plus. Let me just remind you, this means plus tensor product plus. I'll make this an upside down Spanish question mark. But it doesn't work. Okay, so let's actually just work out what it does make. Actually, you should probably know what happens if you fire a plus and a 0 into a C0 gate. That's sort of our most favorite move in quantum. But right, I mean, if you start out with plus, which is 1 over root to 0, plus 1 over root to 1, and then in this picture, like we kind of attach a 0 to the bottom. Okay, so we get 1 over root 2, 0, 0, plus 1 over root 2, 1, 0. And then once we do the C0, well, the first part of the state is unchanged. The second part gets changed to 1, 1. Okay? Which is the famous EPR pair, but it's not this. Okay, so this was wrong. Okay, this is the thing that has 4 amplitudes that are all equal to a half. Okay, and this only has 2 amplitudes equal to 1 over root 2. Okay, so just a C0 gate does not work. And in fact, the no cloning theorem says that nothing works. And just kind of repeat this calculation in generally. If you have alpha 0 plus beta 1 coming in, well, you attach that 0, and you get alpha 0, 0 plus beta 1, 0. And then in the C0, you get alpha 0, 0 plus beta 1, 1. Okay, that's what you actually get if you plug a general state into this device. And to write these as 4-dimensional vectors, I'd like to do that. This would be alpha 0, beta 0.
Is that 0, 0 beta?
Well, this one is. What I'm trying to say is, yeah, so actually, yeah, this is not this. Yeah, so let me say this is this. This is like the pre-C0 bit. Actually, no, let me do the natural thing here. Let me write down this thing, which is 0 beta. And it's not the thing that we wanted to get. And what is the thing that we wanted to get?
Alpha squared, alpha beta, alpha beta, beta squared.
Yeah, alpha squared, alpha, beta, beta squared. Okay, that's equal to this state tensored with itself. Okay, so this C0 doesn't work, and the theorem, the no cloning theorem, says that nothing can work. Okay, so let me give you the proof of the theorem. Well, actually, I'm going to kind of do two versions of the proof. And the first version is the intuitive, albeit incomplete proof. Okay, so this is not a perfectly rigorous proof, but it conveys the right idea, which is this. So, hypothetically, you're trying to take a machine that takes in one qubit in the state alpha 0 plus beta 1, and then somehow it goes through some machine, and out comes, ideally, well, this vector, as we saw, alpha squared, beta, beta squared. In other words, the two copies, unentangled copies of this. And, well, I mean, particles, this particle has to come from somewhere. So let's need to get another particle into the picture. And without loss of generality, you can assume that this particle starts out in state 0, because if you want to start in some other state, well, just have the machine convert 0 into that state. Okay, and so therefore, collectively at the beginning, the state will be the tensor product of this state and this state, which is exactly what we had here. So it's alpha 0, beta 0. So if this is the picture, then the cloner would be trying to implement this map that takes any vector that looks like this and converts it to any vector that looks like, well, converts it to that vector. But you might just say, I mean, and this is true, this is not a linear map. I mean, look, there's like squares in here. Like, you should not be able to get that by like, this is supposed to be like a unitary transformation, which in particular is a linear transformation. It's supposed to be like a matrix that you multiply against this vector to get this vector. Well, you cannot get squares by linear transformations. So intuitively, that's the end of the proof. And that intuition is fine. But it's not really a complete proof. For a couple of reasons. Actually, anybody spot some problems with this? Yeah?
How do we know that we can't build anything that's not a linear map?
Well, in some sense, it's like a law of quantum mechanics that if you have like a bunch of particles and you're making a transformation to them, then that transformation is not just a linear transformation, but a unitary transformation. However, yeah, so there are a couple of catches to that. One of them is there is measuring, which is like a different thing, which the machine maybe could do, and that's not a linear transformation. One sec. There's also another aspect to what you're saying, though, that's also true, which is that one thing that the machine could do, which is not just captured by saying like, oh, it's supposed to be some 4x4 linear transformation from this to this. The machine could like require to work maybe a few more qubits in the state 0. These in quantum computing are called ancillas, and maybe it somehow needs maybe 2 more ancillas in the state 0, and it outputs not just maybe it outputs not just psi tensor psi, but maybe tensor with 0 and tensor with 0. And then it's like, okay, and then it says, now just feel free to throw these 2 qubits in the garbage. Okay, I mean, maybe there could be a cloner that worked like that. And it would actually be some linear map that took, instead of this 4-dimensional vector, now it would be a 16-dimensional vector to this 16-dimensional vector, and then threw out the last 2 qubits. We'll see that that's also not possible. And I mean, it still seems to face the same problem, which is that, if you wrote down the definition of this vector, it would kind of look like this. It would just have some more zeros in it. And it would still seem to have like some squares in it, which don't seem possible to affect by a linear transformation. Yeah?
My question was kind of similar to what we just talked about, but are we just only considering the case where the second bit weight hash is only 0? Is that like without loss generality?
This one here?
Yeah.
Kind of, yeah, because I mean, let's say your machine wants, you know, some extra, these are called ancilla qubits to work with. I mean, if you really wanted it, you know, if you got it to work not with a 0, but with like a 1 coming in, then that's okay. I mean, you could have just assumed you had a 0 came in, and like the first thing your machine does is put like a little NOT gate here. So basically, if it wanted it in any particular, you know, 1 qubit state, without loss of generality, you can assume the machine accepts a 0 coming in, and then like does a little 1 qubit circuit to get it into the desired state. Yeah?
Why is measuring not a linear transformation?
Well, I mean,
Doesn't it only rotate?
no, it doesn't only rotate. First of all, I mean, it doesn't even exactly fit the picture because like it not only changes the state in like it changes the state in like not even a deterministic way. So it's not even like a deterministic transformation, let alone a linear transformation. And it also generates like this classic input, like classical information, like the readout on the you know, measuring device.
It doesn't square things though, right?
No. The thing is that the transformation the measurement does, it's like linear in your sense, but the transformation that is linear depends on the alpha and beta of the qubit you're measuring, right? And if you allow transformation to depend on alpha and beta, there is a linear transformation that takes that one to that one, right?
I'm not.
You can construct a 4x4 matrix that involves alpha and beta that takes that vector to that one.
That involves alpha and beta, yeah, but that's a different issue in the sense that like this is like getting at the issue that like this has to work for like an unknown, it has to work simultaneously for all alphas and betas. It has to be like one fixed thing which works for all alphas and betas.
Right. But
Like
that's
if
what measuring is doing, right? Like
no.
It actually depends on alpha and beta, like the out, right?
Yeah.
Yes.
Sort of, but I mean it's not even like a deterministic map for one thing. Yeah.
If we tensor psi with itself, we get that.
Yeah.
So that's a linear transformation.
What is a linear transformation?
We changed the dimension altogether, that's not linear.
There's linear transformations that change the dimension. That's not a problem. Although, I mean, unitary transformations don't have this property. But you're right, this aspect of like adding in like a new qubit in the state 0 is not a linear transformation, yet it is a thing you can do. We're actually going to study the most general class of things you can do, and the most general eventually in the class, and the most general set of things you can do is like take a state, add some qubits in the state 0, do a unitary transformation on the big system, throw some of the results in the garbage. This is like the most general thing you can do. And that's what we're actually even going to rule out here. Yeah.
So we need to do a proof that works for adding any number of extra zeros.
Yeah, it's going to be easy. Well, let me just also like say, I mean, I sort of even tricked you a little bit. I'm not tricked you because you're very skeptical already, which is good. But you know, just saying like, oh look, there's squares there. Therefore, you could not get that by a linear transformation. Even that's not quite right because it doesn't. It's true that there's no like linear transformation that maps 4-dimensional space into 4-dimensional space and does this transformation. But like this is not a completely general vector in 4-dimensional space. For example, these two numbers squared have to add up to 1, or their magnitudes do. So for example, like if I were to say like, oh, take a look at this little transformation that takes a 1 qubit state to this 1 qubit state. Okay, I might say, look, this has like cubes in it and squares, so like obviously it's not a linear transformation. But in some sense, for the purposes of quantum, it is, because I just wrote this following thing in a complicated way. Alpha beta times the scalar. Let me assume alpha and beta are real. Alpha squared plus beta squared. All right? But then if this is a qubit state, then this is just the number 1. So for real amplitude qubit states, the identity transformation does this. Okay, so it's not just enough to say, this is like a technical math point to say like, oh, look, there's squares, therefore it can't be linear. Except that it is true, that it turns out to be true that there is no linear transformation that does this. Okay, so now I want to give you a more proper proof, but I am going to omit the possibility that your cloning machine could have measurements in it. It's actually not hard to upgrade this proof to allow for that. So we'll later see when we study quantum computing, there's a a simple principle called the principle of deferred measurement, which is very easy to show, that says that like whenever you build like any kind of machine that has measurements like in the middle, there's like an equivalent machine that has measurements like right at the end. And then once you use that fact to take any hypothetical measurements in the middle to the end, it's then not hard to see from the proof I'm about to give that like that cannot help you make the cloning machine. Okay, so I'm not actually giving you like the completely full proof because I'm skipping measurements, but trust me, it still doesn't help. Okay, so the real proof looks like this, or the realer proof at least. We say suppose there exists even this more general potential cloner, okay, that takes in the first input like any qubit state psi, and then perhaps the cloner needs to use like some more additional qubits, which without loss of generality can be assumed to be in the state 0. And then the cloner outputs 2 copies of psi, plus it can output some more stuff, which is kind of like garbage, and it might depend on psi. But the point is these things should all be unentangled. Okay, so that you can then just like throw the garbage out. It doesn't affect this, nice 2 unentangled copies of psi. Okay? So suppose such a thing exists, and this thing has to be a unitary transformation U. Yep?
If the garbage is entangled,
Yeah.
if you just put it away and never touch it again, isn't it like it's not entangled?
Now, this is something we talked about before. Again, it's not very easy to see all these things without getting into talking about mixed states, but let's say you have this situation, and like you consider the first bit like the real bit you cared about, and the second bit was some garbage. If you now like throw away the second qubit and you like promise like you'll never talk about it again, then what is the state of the first qubit? Well, one can actually ascribe to it a state, but it won't be a pure state like we're used to. It will be the state 50% probability of 0, and 50% probability of 1. This is a probability distribution of our classical states.
Can
So-
you explain why it's not actually like just 1 or 2? Why it's not plus?
Because basically at a high level, I mean, well, first of all, it's sort of the rules, but like if you promise that like, Bob is holding onto this qubit and like you're never going to see him again, he's never going to affect our lives again, then one way I like to think about it is like you can just imagine that Bob measured his qubit. Because like maybe he did for all you know. I mean, he did it in the privacy of his own home. He can do that. And if the Bob were to measure the second qubit, then the result on Alice's side would be a 50% chance of this pure state 0, 50% chance of the pure state 1. And so like that, if Bob really never gets involved again, this is the correct way to model the state of the first qubit. But like that's not plus. Or similarly, if like this junk were entangled with this stuff, and then we're like, we're going to throw it away, we're promised we're never going to look at it again, mathematically it's the same as if we had measured all these qubits. And then if we do that, and it's not entangled, and it is entangled with these guys, then instead of just being left with a nice psi tensor psi, you'll be left with some potentially weirdo probability distribution over something that's different things which are not psi tensor psi. Yep?
But what if instead of Bob takes the qubit home, what if you keep the qubit in a box in the lab and you know that no one is touching it, no one's measuring it, and you know that it just exists there?
It's the same. Like for all future analysis that we know how to analyze all future things that would happen involving these qubits. And for all future experiments that you could do that only touched these 2 qubits and measured them, all the outcomes you could ever see or do would be indistinguishable from what would happen if Bob did measure these qubits and you did the same experiments. So that's something you can like have to mathematically check for yourself, but it is the case. Okay, these things take some getting used to, so it's good to, yeah?
Very quickly, so that qubit that you have
Yeah.
is no longer in superposition, is that what you're saying?
Which qubit?
Like the qubit you have, and then you throw away another qubit, and entangle qubit. I'm sorry.
Like in this case, for example?
Yeah. So if you threw away one, like Bob like takes it away,
Yeah.
the one you have is no longer in superposition? Is that correct?
I don't exactly know what you mean by superposition. I mean, does that mean having more than one non-zero amplitude?
Yeah, it's no longer a wave function, it's just 50% 0 or 50% 1.
Yeah. I mean, yeah, if you, this is the correct mathematical description, basically, of the first qubit state, if you were like, throw the second one. And this is a classical probability. And yeah, if you want to use the words, this thing is not in superposition, which is fine with me, then perhaps you would say that this whole thing is not in superposition. But I would just prefer to say, like, it's this. You can use whichever words to describe it you want.
So it's no longer 1 over root 2. So that's sine of 0.
No, like it's definitely not, this is definitely not the same state as this. Yeah. For example, it's very easy to distinguish this possibility from this possibility. Can somebody see how to do it? Yeah.
You can do one of the transformations that basically reverses the sign of the second amplitude.
Yeah.
And so if in the left possibility you get plus goes to minus, in the right possibility you have minus 0 or 1.
Well, then what?
No.
You still can't just like look at the state, I mean, to see what it is. Yeah.
Could you measure in the plus minus basis?
Yeah, if you measure in the plus minus basis, I mean, you get a good probability. So if you measure this thing in the plus minus basis, then 100% of the time you'll see the readout plus. If you measure this in the plus minus basis, then half the time you'll see plus, half the time you'll see minus. So you have like a reasonable chance of telling the difference between these two states. Okay, good. So let's get back to this picture. Good. So suppose this hypothetical cloner exists, and as I said, it's one with no internal measurements. Okay, so just to say in words what it does, I mean, it's saying that if you apply U to psi tensored with, a bunch of copies of 0, let's say there are n minus 1 here, what you get is psi tensor, some very large n-dimensional vector, 2 to the n minus 2 dimensional vector, that depends potentially on psi. And this is supposed to hold for all qubit states psi. Okay, so I'm just going to apply this fact that supposedly exists to 3 different states psi and then get a contradiction. In fact, those states are going to be 0, 1, and plus. Okay, so therefore, U of 0 tensored with a bunch of zeros, that's some funny notation for this, is 0, 0 tensored with some vector called f of 0. And U of 1 tensored with a bunch of zeros is 1, 1 tensored with some big vector, the garbage vector. Okay, this is all, eventually the last line is going to be like, which is a contradiction. Okay, this is a proof by contradiction, should have said. And I'm going to imagine applying it to plus as well. Okay, and what we get is plus, let me write it slightly more elaborately, like this. We call these 3 statements A, B, and C. Okay, so these are 3 equations which are apparently true. So I'll now just form the equation 1 over root 2 A plus 1 over root 2 B. Okay. Okay, and so what do I get if I add 1 over root 2 this plus 1 over root 2 this? Well, it's a U applied to 1 over root 2 this plus 1 over root 2 this, which is actually plus. Okay, so on the left-hand side, I actually get U plus. This is using, these nice linear algebra properties of tensoring, linearity basically. And what do I get on the right side? Well, I just get this combination. So I get 1 over root 2, 0, 0, tensored with the 0 garbage, plus 1 over root 2, 1, 1, tensored with the 1 garbage. But equation C tells me that this is equal to this. And let me just expand out what this is. So I'm going to use the fact that this is 1 over root 2, 0 plus 1. And I'll use it here as well. And I'm just going to multiply out. Okay? So this C is also equal to half 0, 0 plus a half 0, 1 plus a half 1, 0 plus a half 1, 1 tensored with this plus garbage. Okay? So if all these equations are supposedly true, then this state should equal this state, which looks extremely implausible, probably, and indeed it is impossible. So, and here's a quick way to tell these are not the same state. So, but these are not equal. Because imagine measuring the first 2 bits. Okay, well, what would you get in this case if you measure the first 2 bits? This is all like just stuff in the 3rd through nth components, so it doesn't affect. This is all the components of the state that start with 0, 0. This is all the components of the state that start with 1, 1. So you'll see 0, 0 or 1, 1, probability a half each. But if you were to measure the first 2 bits here, you'd see all 4 possibilities with a quarter each. And that's different. So it's like a quick way to see that these 2 states are definitely different. Okay, just as a remark, getting back to an earlier question, we didn't use that much about the cloner here. In fact, we only used the fact that the cloner works correctly, supposedly, on 0, 1, and plus. So for example, this shows that not only can you not have a cloner that works for all states psi simultaneously, you can't even build one that works simultaneously for 0, 1, and plus. Yep?
Does this also then show that you can't build it for any set of linearly dependent states?
I think so, yeah.
Same argument.
Yeah, I think so, yeah.
Can you prove that we cannot do it just with 0 and plus?
That's a good question. I didn't think about that before. To prove that you can't do it with just 0 and plus, I think it's definitely true that you cannot do it with 0 and plus, and therefore one can prove it. Can I prove it on the spot right now? Well, I don't know. It shouldn't be that hard. Let me think about it. But it's definitely true that you can't build a cloner that only works with 0 and plus. In fact, in some sense, did you prove something like this in your homework? Maybe. Yeah, okay, it's not clear. I was thinking about how you could use a homework problem to convince yourself that it's true. Anyway, it is true that, yeah, you can't even get a cloner that works just for, let's say, 0 and plus. Okay, so let me just say in words something about a classical comparison with this. Yeah?
Can you clone with like some probability?
Yeah, there actually is work on that. Like, what if you're like, give up a little and you say, well, I want some like device that clones, but maybe not perfectly. Like maybe with some probability it clones successfully. There's research on that. Yeah. Actually, we're supposed to think about that at some point, Kostin. We never. I think it's on our to-do list. Yeah, that's a good question.
Can you also a little bit convince why, if you do any transformation that you can do, is only a linear one?
It's a law of quantum mechanics that like the only operations that can transform qubits, aside from measurements, are unitary transformations.
But then, the law comes from somewhere, right? Like.
It's axiomatic for the
Oh,
mathematical.
for the mathematical model, right?
Yeah.
But like in physics, they somehow convince themselves there is no other, right? Because like even this statement is not true, right? Because you can do measurements, which are completely different kind of operations. Like they're non-stable, etc., but they're still different from linear. So maybe there exists some other transformation that you can do.
Well, it's a little bit like you're saying like, yeah, the physicists convinced themselves that F equals ma, but like maybe there are situations where force doesn't equal mass times acceleration. I mean, they kind of, they found these rules like the unitary transformation and measurement that explains everything. And in fact, eventually, I keep saying this, like maybe it should go towards the beginning of the course, but we're actually going to eventually, when we start studying like mixed states, we're going to see one formulation where there's just like one kind of state, a mixed state, and there's just one kind of transformation that you can do, which is sometimes called a quantum channel, which simultaneously incorporates, it's like one mathematical framework that includes measurements and unitary transformations, and indeed like all physical things that you can do. But really, as it turns out, all physical things that you can do are like measurements and adding in some qubits in the state 0, deleting some qubits that you've already created, and unitary transformations. Yeah?
I'm pretty sure conservation of energy is enough. Like, you take like a Hamiltonian operator, which is the measurement operator for energy, and you can't really increase energy in a system by itself. And so that operator has to be unitary. I think you can make a similar parallel for all other operators. That's my guess.
Yeah, I don't know. I mean, I'm not so sure, but maybe. I mean, at some level, you just have to, for some things, like, we said that, like, well, the state of a qubit is like a unit vector in complex space. Like, you can reject that, and you're like, maybe it could be something different. And it actually, in some sense, it can be something different. It can be like a probability distribution over such. But like, if you accept that, and then you accept that transformations have to be linear, which, why should they be? I don't know. You just have to accept that. Then, like, the only linear transformations that preserve this are unitary. So, just telling you, like, the laws of math that apparently, are consistent with actual experiments. Let me quickly, I don't want to spend too much time in this part, but let me quickly talk about a classical comparison to this no-cloning theorem about cloning biased coins. Okay, so like let's say somebody comes along to you and they have a coin, which is heads or tails, but like it's not necessarily a 50-50 coin. Maybe it's 80% heads, 20% tails, maybe it's 50% heads, maybe it's 15% heads. You're not sure. They just give you this coin. And they want you to do the same thing. They want you to build a physical machine that like accepts this coin as an input and then produces or builds, let's say, 2 coins that are both biased coins, and the bias of the output coins is equal to the bias of the input coin. Okay, so you want to clone this biased bit generator. So, I mean, you could think about that. Like, how would you build that machine in real life? Well, one thing you could do is like maybe like, what is the study of measurement? Like stoichiometrics or something? Like you could like just measure physically measure it, or like you could weigh the coin, or you could try to see like, I don't know, what the bias should be based on just examining it. I don't know how well that would work in practice, but that is something you cannot do with a quantum state, right? I mean, this is kind of one of the things we know about quantum states. Like, you can't just like look at them and find out what the amplitudes are, right? So maybe in the real world with an actual physical coin, you could like look at the coin and try to figure out what the heads and tails probabilities are, but this you cannot do with a quantum state. I mean, the only thing that you're literally allowed to do with a quantum state to get information from it is like measure it in like the technical term of measure. And that's pretty much exactly the same as the action of flipping a quantum coin. That's like measuring the coin in a quantum sense. You flip it and you get a classical bit of information, 0 or 1, which gives you some information about what the true bias of the coin was. Now again, if this were real life and you actually had to make this machine, you would have the machine take in this coin and maybe flip it and then see if it was heads or tails. And you would probably then have it like flip it again and like flip it again and like flip it 1,000 times. And this would be another natural thing to do, like flip it like 10,000 times, count how many times it came up heads. This would give you a very good estimate of its 2 amplitudes. I mean, the probabilities it's heads or tails. And then like once you were like, okay, I think this is pretty much an 8317 coin, you would then like have some separate part of your machine that like, you know, built a coin to the 8317 specifications, and it could spit out a bunch of those. And this is also something that you cannot do in quantum because like you cannot flip a quantum state again, right? We know that like when you measure a quantum state once to get some classical information about its amplitudes, like then it's, you know, collapses to a certain thing, and like remeasuring it will not help. So somehow the right classical coin analog of the quantum state is like a coin where you can't really like study it with your eyes, and you can flip it, but you can only flip it once. Okay? So I'll just write that slightly. This is a pretty good actually analogy to have in life. A quantum state, a qubit state, is kind of similar to a one-time flippable coin. It's not quite the same thing, right? Because this is defined by two non-negative numbers that add up to 1, the heads and tails probabilities. This is defined by two numbers whose squares add up to 1, okay? And instead of unitary transformations, these have stochastic matrices. But other than that, it's sort of the same story. And in fact, if you really, you know, tie your hands a little bit in real life and assume that like, okay, this machine you're trying to build to clone these coins, you know, the only operation it's allowed to do is flip the coin one time, then actually you feel it's much more like believable and natural that like it's not possible to clone such a thing. And it's true. You can actually literally repeat the same proof pretty much and deduce that there's no, like a no cloning theorem for probabilistic bits for like these kinds of coins. Because I don't know, like what are you going to do? Like you can flip it one time, it comes up heads, you're like, well, this coin is probably a coin that's biased more towards heads, probably, but like how are you going to produce that, you know, bunch of copies of that coin? And similarly, like if somebody promises you, well, I mean, the bias is not any number between 0 and 100%, like it's either a 100% heads coin or a 100% tails coin, well, that's a case where you can clone, right? Then you just have to flip it one time, you find out if it's 100% heads or 100% tails, and then you can make lots of copies of that. And that's similar to how here, like, you know, if you're promised that the input qubit is either ket 0 or ket 1, you can clone that. By the way, let me also just, while we have this on the board, and I can say in words, in real life, right, I mean, the actual coin is not one-time flippable. You can flip it a bunch of times. And so a natural thing you could do, you know, especially if you're trying to build this cloning machine, is, you know, flip it like, you know, flip it n times, and then like, you know, there'd be a simple way to aggregate that information and get like an epsilon accurate estimate of the coin's bias. You know, basically actually just output the empirical fraction of time that ended up heads. Simple. And sometimes we call this task learning. I mean, it's like a little learning an unknown distribution on 1 bit. And you know, although quantum states, you know, they're like one-time flippable coins, you can actually imagine making an analogous situation where instead of just getting one copy of the state, you get n copies of the state. So somehow, maybe you have like a machine that generates particles in an unknown state psi. And so you can imagine, you know, a situation where you get like n copies of an unknown state psi. Okay, but what does that mean? It means, you know, a state like psi, tensor, etc. And that's like getting like n copies of a one-time flippable coin, sort of the same thing. You can imagine maybe under this situation, I could try to learn the two complex amplitudes of psi by somehow measuring this in a clever way. And that is possible. And in the quantum case, for some crazy reason, they call it quantum tomography. They should have just called it quantum state learning, but this is the phrase you'll see. And that's actually the part of quantum computing and information that I like work on for my research, like algorithms for quantum tomography. And we'll talk about this problem later in the course. Okay, any questions?
But when you know the quantum state, it's the same. You cannot distinguish for like plus and minus, like positive and negative. Like let's say alpha versus minus alpha, or like alpha versus I alpha. Just
That's right, yeah. You cannot distinguish it up to a global phase. So the most correct setting for this problem is in the setting of mixed states, where we're eventually going to get a mathematical formalism that exactly has like two states have different mathematical representations if and only if they're distinguishable. Yeah.
Should we understand at this point why this limitation is important?
Which limitation?
I mean, that we cannot clone things.
Oh. Yeah, that's what I'm going to talk about now. Good. So, well, first of all, you should think of it as something that's like maybe not necessarily that surprising if you compare it in your mind to like unclonability of one-time flippable coins. But actually, like the next 2 or 3 things we're going to talk about are like almost like responses to the no cloning theorem. So the thing I'm going to talk about for the rest of this class is the quantum teleportation, which is something that looks kind of like cloning, but isn't cloning because cloning is impossible. And the next thing we'll talk about next time is a situation in life where you literally want objects that cannot be cloned. And that's quantum money, right? So if you're designing money, you want to make it such that like once you have a copy of a dollar bill, you cannot make like 2 copies of that dollar bill. And well, I'll tell you the story of quantum money next time. It's very interesting. But it's actually like a positive, use of quantum based on the no cloning theorem.
are we going to talk about it?
Yeah, we'll talk about it next class. Okay, so I want to talk now for the rest of this class about quantum teleportation, which is an interesting thing that you can do. It's looks a little similar to no cloning, but of course, as I said, there are things that you can do that look a little bit similar to cloning, but aren't cloning. So this is also a thing that has like a very, cool looking name. I mean, the people that found this, which was actually some quantum computing people, pioneers like Bennett and Broussard, and some quantum info people. They discovered it actually in 1993, and they gave it a very cool name, which is, smart from a marketing perspective. Yeah. I should also mention that it's pretty cool. It's from like 1993. Like maybe even some of you were alive in 1993 when this happened. Like even after like 80 years of quantum mechanics being around, this like kind of like magic trick, they only discovered it then. So we're learning some kind of modern stuff. Good. So it's going to be like another like magic trick, like the CHSH game that like 2 parties, Alice and Bob, can do. And one thing that I should emphasize is, although it's called teleportation, it's not going to involve like matter being like instantly moved. It's going to involve information being instantly moved. Okay? So in some sense, so like a quantum state will be teleported, and you should also like not get like all freaked out about like I shouldn't have said instantly moved actually. Let's say very quickly moved. You should not get freaked out about like faster than light, travel or like causality being ruined or anything, because this magic trick is going to involve Alice and Bob exchanging classical information. So it takes them some time to do that. Which is why I like to imagine instead of like teleportation between like Mars and Jupiter, like I'd rather imagine like teleportation between Wien Hall and Gates. So that's what we'll talk about. So good. So let's imagine that here is Gates, and here is Alice. She's got an office in Gates, and she's messing about in her office with her quantum gadgetry, and somehow she comes across this particle, qubit, in state psi. But she doesn't know what the state psi is, but she finds a particle, and it has some quantum state, of course. Okay, so psi is going to be a qubit in an unknown state. Okay, and there's also Bob over in Wien. These 2 characters are friends. And Bob really loves, particles in unknown states. He loves, just investigating and stuff like that. So Alice wants to like give this particle, he wants to give this state to Bob to play with. So how's she going to do this? Well, I mean, one thing she could do is like get out of her office and like walk over to Wien and be like, here you go. But that's too annoying. She's too lazy for that. So in quantum teleportation, here's how it's going to look. So Alice is going to sit in her office and do something quantum-y involving psi. Okay, and then she's going to get out her phone and she's going to like text Bob a little message. Okay, so she'll text, and this will actually be a 2-bit message, classical bit. So she'll text Bob like 2 characters, like maybe 0, 1. Okay, and then Bob will get this text message and he'll do a little something quantum-y in his lab, and ta-da, he'll at the end of that be holding on to a qubit in state psi. Now I have to, yeah. Now there's a couple of things going on here. First of all, at the end of this picture, this actually better be gone, because, you know, if Alice still also had a qubit in the state psi and they were unentangled, then we would have violated no cloning. Like Alice would have psi and Bob would have psi, and it worked for any unknown state psi. So it will be the case at the end of this magic trick, Alice will no longer be holding on to a qubit in the state psi. Just as if she had actually, you know, walked over to Bob's office and gave away the particle. And there's one more aspect to the trick, which I didn't mention yet. But it's the same in the CHSH game. You have to assume that before anything started, Alice and Bob shared an EPR pair. Okay, so how are they going to do this trick? Well, you just, you know, Alice and Bob are friends, so, you know, they're always talking. So let's just assume at some date they prepared a bunch of EPR pairs, they each took one particle, and they just stored them in the fridge in their office for future, you know, stuff like this. So we're going to assume like Alice and Bob share, you know, one EPR pair before things start. Okay, so yeah, let me draw a little picture of this story that's a little bit more precise. So here we have Alice, and somehow she gets a hold of this particle in an unknown state. And, you know, before anything happened, here's Bob down here. They had this EPR pair. Okay, remember that's 2 qubits in this state, 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. Okay, and Alice holds the first particle and Bob holds the second particle. But like, this is like, somehow this horizontal line reflects the fact that this is like Bob's office down here and this is Alice's office up here. Okay. So somehow Alice is going to do something here, and then at this point she'll send a text message to Bob, which is 2 bits. And then Bob, actually after receiving the text message, will do like something here, and out will come psi. Okay, so sometimes people summarize this story with this little phrase: 1 E-bit, that's like an entangled EPR pair, plus 2 classical bits is as good as 1 qubit. Well, this phrase, I guess, just reminds you that you need like 1 EPR pair and transmit 2 classical bits of information, and you can use that to transport a qubit. And I just wrote this down because like on homework 3, problem 3, you saw something that looked similar to this, right? Except it was like 1 qubit and 1 entangled pair like gave you 2 classical bits or something. That thing, by the way, I didn't use the title, but that thing is from homework 3 is called super dense coding. So you can Google that if you want. One thing I should also want to stress here, which makes this, you know, even more interesting than it might look at first glance, is imagine that Alice even knew psi. You know, she generated psi. It was like some arbitrary state, but like she knew exactly psi. She knew the 2 amplitudes, alpha and beta. Then this would still look kind of amazing. She transmits only 2 classical bits to Bob, and suddenly Bob gets like a perfect copy of psi. I mean, the natural thing to do is she would say like, okay, Bob, I'm going to tell you the 2 amplitudes. The first one is like 0.5632984, blah, blah, blah. Theoretically, she needs infinitely many bits for that. The second I guess she doesn't have to say that. Well, she does have to say the second amplitude because, you know, whatever, it makes a difference. So it's minus something, 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 something. Yeah, so you know, without this piece, it even looks amazing if Alice knew the description of psi. Somehow she transmits that to Bob with only 2 classical bits. Okay, any questions about the setup? Yeah.
Are amplitudes algebraic? Like, would you get 1 over pi amplitude?
I mean, in principle, it's like the same question as like, can you build a piece of iron that's like 1 over pi meters long? Like, I guess you would say like mathematically it's natural to like say that, yeah, you could. Although both there and also in the real life of quantum states, like at some point, perhaps like you cannot get this exact precision. Well, yeah, like in the mathematical model, there's no reason to disallow like any arbitrary complex number as an amplitude. Okay, so one way that you can explain quantum teleportation is just like draw the circuit here, but like it's quite unmotivated that way. And in the Umesh Vazirani's videos, he explains it in a way that I liked a lot. So I'm basically just going to copy his explanation here. So this process is going to happen in 2 parts. And in the first part, we're going to somehow imagine we'll first imagine that Alice and Bob can somehow do, I'll say, a distributed C0, by which I mean they can, by sitting in their offices, like Alice is one particle, Bob is another particle, we'll just imagine that somehow they can magically put their particles through a C0 gate. Okay? Now, later, we're actually going to see how to implement that stage. But for now, like, let's just imagine that they could do it. And the reason one would imagine this is like C0 is the thing in life, in quantum, that's somehow most similar to copying. Okay? And in general, like, one aspect of quantum teleportation that's going to be interesting is we'll show how to implement this. And that's actually kind of useful for practically building things to like see a way that distributed parties can like do a simple transformation on their 2 bits together. But let's first imagine this. But then ask ourselves, well, why does that actually help? So what I'm saying is, like, let's imagine, hypothetically, that Alice, starting with some arbitrary state, and Bob, let's say in this imagining he just has a qubit in state 0. Let's imagine that, again, like, somehow they can do this. Okay? Well, that doesn't accomplish the magic trick, because, I mean, at this point, they have particles in this joint state, as we know. We saw this at the beginning when we imagined that C0 is kind of, could be like cloning. It doesn't work. It gives you this. OK, but let's assume that they can do that. But now what? Well, at the end of the day, right, like, Bob is supposed to be holding on to a 1 qubit state, and Alice is supposed to be holding on to nothing, or not that state. So the next logical step, presumably, would be that Alice would measure her particle. That's one way to get down to like 1 qubit on Bob's side. But, well, you can see that if Alice just measures her particle at this state, at this time, nothing good is going to happen, right? I mean, she'll measure. Well, then after that, Bob will be, he'll have either 0 with probability magnitude of alpha squared, or 1 probability magnitude of beta squared, which is not good. Bob was supposed to get psi in the end. OK, so Alice has to do something different. But like, how many different things do we know, right? I mean, she's got to measure. Just measuring in the standard basis didn't work. We have like one more trick. Like, what if she measures in the like plus or minus basis? OK, and this is going to work. OK, so so instead of this, what Alice is going to do, let's say instead of saying she measures in the plus or minus basis, let's say she first does a Hadamard to her qubit and then measures in the standard basis. That's the same thing, actually, right? So what will work is Alice is going to, put her qubit into a Hadamard gate and then measure in the standard basis. OK, and let's figure out what happens. So this is the state coming in. Bob doesn't do anything. Alice puts a Hadamard on her first qubit. Well, hopefully you're good at practice on this, and so you are familiar with what I'm going to do mathematically. So at this point, The new state could be written as alpha plus 0. I mean, Hadamard takes 0 to plus and 1 to minus. Plus beta 1 minus 1. But let's just spell out what that is. Okay, so plus is up to 1 over root 2 is 0 plus 1, and minus is 0 minus 1. So it's alpha over root 2, 0, 0, plus alpha over root 2, 1, 0, plus beta over root 2, 0, 1, minus beta over root 2, 1, 1. Okay, hopefully you agree to that. Okay, and now Alice measures her qubit. So this is the state here, and then what happens here after she measures? Well, she sees either 0 or 1. What's the probability she sees 0? Well, you take the squares, all the amplitudes that have a 0 in the first position. So that's this one and this one. Which actually conveniently is 1/2. That's nice. And then Bob, in this case, if this is the outcome, Bob's state collapses to, well, you pick off the components here that have a 0 in the first component, the first position, and then you divide by the square root of that probability, which is 1 over root 2. So actually, nicely, it just turns into alpha 0, 0 plus, well, it does that, but let me just say Bob's part is alpha 0 plus beta 1. Okay, really the overall state collapses to alpha 0, 0, beta 0, 1, but that just reflects that, like, in this case, Alice's state is 0, and it's unentangled with Bob's state. So let me just leave it at that. And hey, presto, that's psi. Great. And what about the probability that she measures 1? Well, it's got to be the remaining probability, which is 1/2. Anyway, that's this magnitude squared plus this magnitude squared. And Bob's state collapses to, well, the piece that has a 1 in the first component divided by root 2, which is alpha 0 minus beta 1. That's more of like a this-shaped emoji. It's almost psi. So any suggestions? Yeah. Okay.
I mean, she knows what she gets, right? So if she send that to Bob, he knows like which of these cases he's in, so he can like flip the second side.
Perfect. That's right. So now Alice gets out her phone, and Alice texts Bob, her measurement outcome. Okay, that's one classical bit. She texts him either 0 or 1. Okay, and if she texts him 0, Bob does nothing. Okay, because he's already in state psi. That's great. And if she texts him 1, then he knows that he almost has psi. He just has to flip the sign on the 1 component. So if it's 0, Bob applies, I don't know if you remember this, but this so-called Z-gate. That's the thing that has this matrix. Or you can say it's the thing that maps ket 0 to ket 0 and maps ket 1 to negative ket 1. Okay, now in this case, Bob has psi again. Okay. So what have we seen? We've seen that if like somehow they did this distributed C0, which we'll get to, then Alice does a little something, texts 1 bit to Bob, Bob does a little something potentially, and voila, Bob holds on to psi. And by the way, Alice does not hold on to psi anymore, right? Alice measured her qubit that started out at psi, and now it's got nothing. I mean, it's got either 0 or 1, and she knows exactly whether it's 0 or 1. So, I mean, it's as if she had nothing, right? I mean, she retains no information about psi at all. Yep?
So where exactly does this C0 take place?
Is it with Alice and Bob both clear?
Well, so far it's like magical, right? It's hypothetical. So we're going to see just now is that using the resources that they have that I already described, they can make this C0 happen without actually getting together physically. Well, what are these resources I've described? What's that? Yeah, mainly the EPR pair. We didn't use the EPR pair yet. Also, we have like one bit of communication that we said we were going to use and we haven't used yet. So now what I will show you is how using that pre-shared EPR pair plus the ability to text one more classical bit of information, they can get the effect of creating this C0 gate between their offices. Okay. So let me draw the picture again. Now Alice has psi, as always. And they also have this EPR pair. And this is Bob's stuff down here. And then, yeah, it's like, OK. So they're not going to leave their offices. OK, so we got to figure out how to do this sort of distributed C0. I say distributed to mean the fact that like the two parties are distributed in space. OK, so we got to do something. And again, it's kind of like, well, I mean, what can you possibly do? There's only so many moves you can imagine. Well, Alice has got to do something, so she's just going to do a C0 between these two guys. I don't know, what else can you imagine? So she takes this state that she doesn't know, and she's going to use that as the control. She's going to like C0 that onto her half of the EPR pair. Okay, hopefully something good will happen. Okay, so we have to exactly find out what will happen. So let's write time 1 and time 2, and we'll just write down what are the states of all 3 particles at time 1 and time 2. Okay, so at time 1, what is the state? Well, it's this. This is what we're assuming is psi, tensored with the EPR pair. We're assuming that this psi that she ran across is unentangled with her EPR pair, her half of the EPR pair. Okay, well, I'm going to literally write this all out. So it's alpha over root 2, 0, 0, 0, plus alpha over root 2, 0, 1, 1, plus beta over root 2, 1, 0, 0, plus beta over root 2, 1, 1, 1. Okay, catch me if I make a mistake. Good, so that's the state at time 1. Okay, what at time 2, after she does the C0 to her own personal bits, which she can do in the privacy of her own office? Well, I mean, we're doing a C0 to the first 2 bits, so we know how this works too. Here, control bit is 0, so nothing changes. Here, the control bit is 0, so nothing changes. In these 2 cases, the control bit is 1, so the second bit flips. Okay, that's the state at time 2. Okay, and well, now what? Well, again, motivated by the fact that, like, we know in the end, like, Alice has to divest herself of qubits, and like Bob is supposed to get qubits. Right now, Alice has 2 qubits, so she should measure something. Okay, and I mean, what better thing to measure than one of her qubits? And then which one should she measure? Well, she kind of just targeted the middle qubit, this qubit. So let's let her measure that. Okay, so what she's going to do? She's going to measure the second qubit, if you will. Okay, in the standard basis. Okay, which is this one. I'll try to underline it. Okay, so she's going to get either 0 or 1. Let's compute the probability that she gets 0. Well, you find all the pieces of the state that have a 0 in the middle, which are these 2, add up their squared amplitudes. Hey, check it out. It's alpha over root 2 squared plus beta over root 2 squared, which is a half, which is kind of neat. And then Bob's, well, actually the joint state, let's say of particles 1 and 3. is, I'm going to omit writing particle 2 because we know for sure it's 0. And it's now unentangled with particles 1 and 3. So I'm just going to not write it. Right, well, it's this piece and it's this piece. So it's alpha, and we have to divide by 1 over root 2. So it's alpha 0, 0 plus beta 1, 1. Hey, look, that's actually kind of nice. That's the thing that they were trying to get by virtue of this like hypothetical C0, right? The whole point of the first the previous thing we described is we started assuming that they could get to this state by some kind of magical C0. And look, now they've got to this state. Like Alice holds the first qubit, Bob holds the second qubit. It's in this state. Okay, and what's the probability that she'll measure 1? Well, you can do the calculation or just realize it's 1 minus this. Okay, and then the state of qubits 1 and 3 is, it collapses to, well, again, you can look back at the original joint state of the 3 particles, pick out all the pieces where there was a 1 in the second qubits, normalize by dividing by 1 over root 2, and what you get is this plus this plus this. So alpha 0, 1 plus beta 1, 0. So again, if this was a happy phase, this is like a questionable phase. But, well, again, we can do a similar thing, right? This is almost good. And you would fix it in the sense of making it the same as this if Bob would just do a NOT gate on his qubit. That would fix it. So that would equal this. OK, so Alice can just text him, right? That's the last resource we were planning to use. She texts the measurement outcome to Bob. And again, if it's, Bob sees it's a 0, he does nothing. If it's 1, then Bob applies a NOT gate to his bit. Okay, which is something he can do in the privacy of his own office. And after this, in either case, Bob and Alice will be jointly holding on to this. And now we're in the position that we were in with the magical C0 gates. Okay, we can do the second half where Alice Hadamards her qubit now and measures it and texts the outcome to Bob. And he either applies the Z gate or he does nothing. Yep?
So does that mean we can sort of regard this like texting information as a controlled something gate?
Yeah.
Where the control bit must be like a measured deterministic?
Yeah, so I don't have time to draw because I want to say something in my last 2 minutes. But if you look at the notes, I'll draw like the whole diagram for this. And it's exactly as you say. A good way to think about it is like you take Alice's measurement outcome. Like in this case, we can do it. So she's going to measure this one. Maybe I can even just fit it in here. And then it's sort of like this texting is like actually doing a real controlled NOT in some sense, but with a classical input to the control bit here, based on what she sees. And then like this, there's a Hadamard, and then a measurement. And then you take that classical output and you do like a controlled Z. Okay, so if you look at the notes, you can see the whole diagram with like a lot of C0 gates and Hadamard gates. And had I just shown you that, it wouldn't have looked too enlightening. But hopefully you saw this. Okay, so let me blurt out a couple of things before we go. First of all, like again, this experiment, they can do it. I mentioned this before, but like in 2017, Jian Wei-Pei's group like literally did this experiment of teleportation between like Tibet and some satellite that was 1,000 kilometers away or something, like teleported a state. So that's pretty great. And the last thing I want to mention is a little topic called entanglement swapping, which I don't have time to really get into, but I want to say it because I want to correct something I said in response to a student question in like lecture 5 or something, where I intimated that like if you have 2 particles, the only way to get them to be entangled is if they're physically co-located. And that was actually sort of a misleading answer. because it turns out, like, we won't do the analysis, but like it's perfectly possible for Alice to teleport a qubit to Bob, where that qubit is entangled with something else. So if you imagine like a three-party scenario now, where like Alice is in Gates, and Bob is in Wien, and Charlie is in Doherty, say. Gates, here's Alice, and like Wien, here's Bob, okay, and here's Doherty, and like Charlie is here. Okay, maybe Alice and Bob are friends, so they definitely have some EPR pairs stored in their fridges. And Alice and Charlie are friends, so they also share some EPR pair. But like Bob and Charlie like don't know each other, they've never talked, they never go to each other's offices, they've never seen each other before. Well, in this setup, Alice can prepare like 2 more qubits, however she wants, entangled, so they can be like another EPR pair or like any 2 entangled qubits she wants. And by doing this teleportation protocol twice, once with Bob and once with Charlie, she can like transfer this state to Bob and this state to Charlie. And now Bob and Charlie will hold this entangled pair. And it happened even though like Bob and Charlie never physically interacted. Albeit they did both physically interact at some point with Alice, or somehow they got EPR pairs between them. And Alice made a text to Charlie and Alice made a text to Bob. But nevertheless, I mean, Bob and Charlie never got together, but somehow they were teleported to bits that are entangled. Yep?
They also had to sacrifice the entangled pair between Alice and
Yeah, that's another thing. I didn't emphasize this, but like this teleportation like burns like your EPR pair. That's true.
But makes sense. You see, like Doherty and Wien are connected.
That's right. Yeah. So in fact, this also shows that like EPR pairs are like universal for entanglement in the sense that like if you have like 10 people and you want them to hold on to like a 10 qubit super entangled state, you can have Alice, who's like a dealer, like prepare that 10 qubit entangled state herself and like teleport 1 particle to each person, and then they hold on to that state. So in some sense, these little humble like EPR pairs that have just involved 2 entangled qubits are kind of universal for like creating any kind of entanglement among a bunch of parties. Okay, great. So next time we'll talk about quantum money, among other things.